Find if path exists. Let's explore the problem a little bit. So there is a bidirectional graph with invertices where each vertex is labeled from 0 till n-1. The edges in the graph are represented as 2D integers. See, this is the edge list, by the way, right? It's not the adjacency list, what we were taking, but this is the edge list. If between U to V there is an edge, there would be a list value that would be given to you. Denotes a bidirectional edge between UI and VI. Okay. Every vertex pair is connected by at most one edge, not more than that. If node 1 and node 2 are connected by an edge, right, then no more similar pairs 1, 2 or 2, 1 would be given inside the list. 1, 2 has been given, no 2, 1 would be mentioned. Not in the repeating time 1, 2 would be mentioned again inside the edge list. That's what they have asked you. Now, based on the edge list, right, that determines the graph, you have to determine if a valid path exists between source to the destination or not. Okay. Can you try doing this? Let's see the example, by the way. The overall graph is something like this: 0 to 1, 1 to 2, right? Source is 0, destination is 2. Do we have a path in between 0 till 2? Yes, we have. The answer is true. Okay, there are multiple paths, by the way. I need to check whether I can reach from 0 till 2 or not. If I can, then definitely I would be returning true overall, right? Then this is it, by the way. And right now, this is another graph where 0, 1, 2 form the first component, 3, 4, and 5 form the second component, right? Source is 0, destination is 5. From 0, can we reach 5? The answer is false. Okay, the answer is false. There is no path. So this is how you have to try forming it. How you are going to proceed ahead? Tell me that. Any ideas that I may get?
Traversal korbo, DFS traversal.
Okay, if I try, let's take this example, right? If you start off from the source of 0, you start the DFS traversal. Then what will happen? I can explore 1, I can explore 2. From 0, I can explore 1 and 2. I can never reach the node 5. Am I correct? So if starting from 0, I can never reach 5, that means there is no direct path existing, right? Am I correct? Fine. So straightforward it is, by the way, that I have to start DFS traversal from the source. And while making the DFS, if I can reach the destination, right, there is a path existing between 0 till 5. If no, then the answer is false. How would you code this, by the way? It is quite straightforward it is, by the way. How would you code this?
প্রথমে adjacency list বানাবো.
Yes, we have to make the adjacency list first, right? Okay, so let me, we can do this with the help of either TFS or VFS, anything works. Since we don't have any kind of BFS implementation so far, let's solve that with the help of BFS as well, right? You also get to know that how we can implement BFS, and accordingly, the problem will also be solved, right? Okay, then. So what we require first? Adjacency list. How would you declare that? Vector of vector. Am I correct? Of integers, by the way. And this is going to be ADJ. How many rows and columns? N rows and columns are going to be there. Each row is filled with an empty vector, is it? Each row is filled with an empty vector, is it? Okay. Then what else I am required to do? So let's convert the edge list in terms of the adjacency list, whatever we have done, right? So for int I, that goes on from 0 till edges dot size, and then afterwards I plus plus. See, each and every edge, whatever we are having, contains another list, right? Overall, this is a bigger list for us. Each and every of the slots of the bigger list contain 2 values, U and V. U is connected to V. This is what it is getting determined as. Okay, so what you are going to do here? What is my node U here? What's going to be the node U here? Tell me, all of you. Edges of I, its 0th element. And what's the node V for me? Edges of I and its first index element. If you are accessing the ith edge, right, it has 2 entities, U and V. So I can just say that access the U from the 0th index, access node V from the first index. That's what we are done with. What else? What else I'm required to do? Can I just say, since this is a bidirectional graph, bidirectional edge it contains, adjacency of U dot pushback node V, and then adjacency of V dot pushback what? Node U. Fine. So our adjacency list is ready. Now how you are going to proceed ahead? Tell me that. Utilizing BFS. How can I try solving this? Tell me.
Sir,
I require a queue. Firstly, I require a queue, and what else? I require a visited.
I
I
visited.
require a visited array, right? Visited, it's gonna be, and that's gonna be a vector again for us, vector of Boolean values, let's say, and it has slots for all the n nodes for me. Let all of them be false initially. Works.
Hmm.
Okay. Okay, fine. Then how should I proceed ahead? Tell me that. Post that, how should I proceed ahead?
So
Can I
কিউর
just
মধ্যে ফার্স্ট নোডটা পুশ করব,
can I just say q dot what?
পুশ
Push the source from wherever I'm starting the traversal, right? Okay, I'm sorry for this. It's gonna be push. Then how can I try proceeding ahead till the time my queue is not empty? Am I correct?
হুম
While not q dot empty, then what will happen? Right now, what is the current node I am exploring? That's present at the front. Am I correct?
হুম
That's present into the front. And then what should I do? Tell me that. Here I can just mark the right before pushing the source. I can say that it has been visited already. Then what I can say is that visited of source, let that be initially false because that's already inside the queue. Whatever is inside the queue, that can be termed as okay, we have visited that, no need to revisit that again. I can just check that, okay.
ট্রু হবে না?
Okay, I'm sorry. Yes, it's true. Thanks for this. If suppose node is equal to that of the destination, then what should I do? Can I just straight away return true from here? Works. Break everything and return I found the destination from the given source from wherever I started off my entire journey of tracing. Then what should I do next? If it is not so, then what should I do? For all the neighbors, right? For all the neighbor that I am having into the adjacency of what? The given node, whatever I'm having, right? Here, what I'm required to do.
কিউতে পুশ করতে হবে।
If suppose the current neighbor, I can just say the visited of neighbor is equal to that of false. Is it true? If the current neighbor is not inside the queue, have not been visited yet, then what I am required to do? I can straight away say mark the visited of neighbor as true, and then I can say q dot push what the given neighbor, whatever I'm having. That's it. Works.
Yes.
Works or not. So this is the thing I am done with. Maybe right now. What else? At the end, I can just say, okay, if the entire traversal of utilizing queue the BFS way from source till whatever nodes can be explored, if we are done with it from nowhere, right, I am able to return true inside the given while loop. At the end, I can try saying that return false. That's it. Nothing else, I feel. Or is it C++? Yes, it is. Can we try submitting this? Let's try running. Okay, compilation error. Okay, I'm sorry. It's gonna be the destination. Let's see. Yeah, destination is it. Yeah, try running it once more. Time limit exceeded, but why is it so? It's gonna be visited. The issue that has happened, by the way. Can anyone let me know what mistake did we do here? I think I forgot to perform the q.pop, right? Once the current node has been explored, take it out from the given queue. Pop it out. That's why we are making a repetition inside the queue. So it got accepted. Let me try submitting this. Happened? Well enough. Any doubts?
Clear.
What should be the time complexity? We just made the BFS traversal, nothing else. We just made the BFS traversal, nothing else. So overall, the time complexity is gonna be big O of B plus C. That's it. Okay. Simple problem this was, so we were able to solve it in less amount of time. Any doubts? How did we do that? Start off from a current node, right? Keep on exploring its neighbors till the time you reach the destination. That's it all. And we are exploring the neighbors in terms of the BFS. Level by level we are exploring. Okay, after making all possible searches, am I able to reach the destination or not? If I am able to reach, straightforward return true. Else, if no way it can be reached, I would be returning false. Fine.
Mm-hmm.
Let's see for other questions, whatever we are having. So find if path exists. That's one of the questions that we have taken right now. Okay. Problem that I can have from Leetcode. Okay, let's take this problem. Find the town judge. Okay. In a town, right, there are n people leveled from 1 to n. There is a rumor that one of the people is secretly the town judge, right? The town judge exists. If the town judge exists, then the town judge trusts nobody. The town judge has nobody to trust. Everybody trusts the town judge. Okay. There is exactly one person that satisfies properties 1 and 2. Both the properties can only be satisfied by just a single person. You are given an array trust, where trust of I equal to that of AI, BI. Okay? So the ith value they are given inside that trust array has individually a list what further contain two values, AI, BI. What does it represent? It represents that AI trusts the person BI. Correct? If AI is trusting the person BI, then definitely AI can never be the judge. Correct? If trust relationship does not exist, right, in trust array, then such a relationship does not exist at all. That means if particular in between two nodes or two people, 1 and 2, suppose that no edge has been given, then nobody trusts any other person. Okay, nobody trusts the other one. Let it be 1, let it be. That's it. So return the level of the town judge if the town judge exists and can be identified, or return -1 otherwise. That's what you are required to find out. How would you do this? So here inside, right, inside the trust array, you are given 1 and 2. That means 1 trusts 2. So what is the scenario that I am getting right now? 1 has trusted 2. 2 doesn't trust 1 back. It's not the case. But 1 has trusted 2. Since 1 is trusting 2, right, 2 doesn't trust anyone. 2 is the town judge for me. Correct? What about 1, 3? I think node 3 is being trusted by 1 and node 3 is being trusted by 2 as well. 1 and 2 both cannot be judges because they trust someone. But 3 does not trust anyone back. So 3 is for me the town judge. Okay. 3 is for me the town judge. Afterwards, suppose again, what the thing they have given is 1, 2, 3, 2 to 3, and then 3 is trusting 1 back. There is a back edge from 3 to 1. So 1 also trusts, 2 also trusts, 3 also trusts. So there, this particular thing can never be no particular person here can be the town judge. Okay. How would you do this, by the way? What is your thought? How would you frame the problem? How would you judge the problem? All of you, tell me that.
স্যার যে নোটটা আনরিচেবল সেটাই আই গেস না
Okay, suppose that there is a trust issue, right? 1 is trusting 2. How can you frame that? Person 1 trusts 2. Can I say there is
adjacency list
a directional edge between 1 and 2? Can I just say that?
yes
1 trusts 2, but 2 does not trust back. There is a directional edge between 1 and 2. Am I correct?
হ্যাঁ
Then further, what can be done? Then further, what can be done? Suppose that 1 is trusting 2, 3 is trusting 2, correct? 2 trust 4, and further 4 trust 5, correct? This is overall the trustiness that has been given to you in terms of the trust array. Then how would you proceed ahead with this? Let's make the graph. 1 is trusting 2, 3 further trust 2. Then what? 2 further trust 4, 4 further trust 5. 5 trust no one. So 5 should be the answer for us. Is it so? Is it so? Can I just say, if you form the adjacency list of this, how that's going to be looking like? 1 has a directional edge to 2. 1 has a directional edge to 2. So into the adjacency list of 1, 2 will be there. 3 has a directional edge to 2. into the adjacency list of 3, 2 would be there. Correct? 2 has a directional edge towards 4. So into the adjacency list of 2, right? 4 will be there. 4 further has a adjacency list. Inside its adjacency list, 5 should be there, right? 5 does not have anything into its adjacency list. All fine? All fine?
Yes.
Correct. So whatever node will be having 0 number of neighbors into its adjacency list, it does not. Since 5 does not trust anyone, it cannot point to any of the nodes, right, with the help of an edge. Getting it?
Got it.
Getting it? So my
Yes.
point is, do we actually require to keep any adjacency list? You may or may not. This is a directional graph, right? This is a directional graph for me right now. 1 is pointing to 2, 3 is further pointing to 2, 2 is pointing to 4, and afterwards, what should I say is that 4 is further pointing to 5. Can I just say, see, if 5 does not point to any other node, it does not have any outer degree. Works? It does not have any out degree for us. All of you agree with me on this. 2 has
Yes.
2 has an outer degree. 1 has an out degree. 3 has an out degree. 4 has an out degree. But 5 does not. Can I maintain an array? Can I maintain an array? 1, 2, 3, 4, 5. All the 5 nodes from 1 till 5 are present into the array. And for each and every node, I will keep a measure how many outer degrees it has. Works?
Yes.
How many outer degrees the particular node is having, whatever node we are dealing with right now. Correct? Okay, so 1 and 2 are connected via an directional edge. 1 and 2 are connected via an directional edge, right? So 1 has, as of now, 1 has a single outer degree. 3 is connected to 2 via directional edge. 2 has, so 3 has what? Single outer degree. 2 is connected to 4 via this edge. 2 has also one outer degree, by the way. 4 is also connected to 5 outer degree. But for 5, there are 0 out degrees. Corresponding to whatever node, right, there are 0 out degrees. I would just take that as my answer. Works? I would just take that as my answer. I don't require to at all keep any kind of adjacency list. Works?
Yes.
Works for everyone? First tell me this. Quite straightforward it is also. How can I try doing it? I can just say, right, vector of integer out degree. Out degree, let there be n plus 1 rows here. All the values are initially 0 because the nodes are numbered from 1 till n. So I have to keep n plus 1 size of the given out degree array. Let's go to 1 by 1. The trust array, whatever has been given to us, I equal to 0, I less than trust dot size, I plus plus. Then what I require to say here? First tell me. What I require to say here? Tell me. What's the node given to me? Let me access that. So I should be saying that trust of I of 0, right? Then INTB, what is it by the way? It's going to be trust. Trust of I of 1 by the way. What else? U is trusting V, right? So there is an out degree associated with U. So I should be saying that out degree of U plus plus. Done. Done. Okay, fine. Let's move on to all the nodes one by one. From 1 till n, whatever I am having, I less than equal to n, I plus plus. Correct. If suppose the out degree of the current node I equal to that of 0, I can just say answer would be equal to that of I. That's it. Nothing else. At the end, whatever is the value of your answer, return that. Any doubts? How did we approach this? U is pointing to V with the help of a trust. What we are assuming in terms of an edge. So out degree of U increases. That's what I maintained. I maintained an array to calculate the number of out degrees a particular node can have. If a node is trusting someone with the help of an out degree, it cannot be mayor or whatever it is, right? The town judge basically. So that's it. Let me try running this. Okay, it all passed. Let me try submitting this. Wrong answer. Why is it so? Anything we did wrong? Why is it so, by the way? Why? 1, 2, 2, 3. Is there any kind of bug here?
3 থেকে তো বাদ নেই, 3টা আনসার হবে।
Our
So আপনি
output is 3, but
2
the
এর জন্য করছিলেন, 3 এর জন্য করছিলেন।
expected is -1, by the way. 3 does not trust anyone, right?
ইয়েস।
Okay, fine, fine, fine. Anything we missed here inside the problem? Something we have missed for sure. What is it? Something we have missed out for sure. What is it, by the way? See for one statement of the question that we overlook, by the way. What is it? The town judge trusts nobody. Everyone except the town judge trust the town judge. Every other node, right, should be having a outer degree to the town judge. All of you agree with me on this? All of you agree with me on this? First, tell me that. Every other node, if suppose the ith node is the town judge, right, from 1 till n, except the ith node should be trusting this particular town judge. That is the ith node for us. So what should be the in degree of this node? Can you let me know? If I say that, okay, particularly x number of people have trusted the ith node, right? But x number of people have trusted the ith node, by the way. Then how many in degrees it should be having? Trust means a node x is actually pointing to y and h to this particular node I. So it has some in degree, by the way. So if node I has to be the town judge, it has to have exactly n-1 in degrees. All of you agree with me? All of you agree with me on this? It should not trust anyone. There should be 0 number of out degrees from this node, but it should have n-1 in degrees. So another parameter we need to keep. What is it? The in degree counterpart, right? The in degree counterpart. So let me keep vector of integer in degree, right? n+1, it's gonna be overall. And overall, there's initially 0 number of in degrees for us. So how should I update that, by the way? Out degree of u plus plus in degree of, tell me, in degree of v plus plus. Am I correct? There is, so v is being trusted with the via the edge of u, right? So there is an inward coming edge corresponding to the node v. So I would be increasing its in degree by 1. Correct? That's it. So if outer degree equal to 0 and what?
In degree equals to n-1.
In degree of I equal to n-1. Then only the condition is true. So that's why then at then we will be returning the answer. Try submitting this. Should be submitted, by the way, right now. Yeah, it got accepted. Any problem? Any problem? It's
No.
just a big O of an approach for us. You are not running any TFS or BFS. You are just checking for the in degree, out degree, and corresponding to all the edges given to you, and you are traversing to all the nodes to check for the town judge finally. So it's a big O of n problem for us, nothing else. Okay. Any doubts? Corresponding to this problem, do you people have any doubts? Tell me.
Clear.
Quite a bit straightforward problem, right? Okay, what else we should take today? Let's take this problem, right? Very important problem. Bipartite graph. Give me 2 minutes. I don't know who was it, by the way. Never know. Okay, read the problem for 2-3 minutes. Then let me know what is coming to your mind. You know about bipartite graphs? You know about bipartite graphs? What is bipartite graph? Tell me, anyone. What is a bipartite graph? Anyone? Okay, go ahead, read this, and then let me know that. What are your thoughts? How we may try solving this? Go ahead, all. Okay, any idea? How would we solve this? What is a bipartite graph? Anyone? What is a bipartite graph? Anyone? This graph is not a bipartite one. Didn't you read about bipartite graphs? What are they?
Forgot.
The graph that can be colored with two colors. Is it that? The graph that can be colored with exactly two colors. This is what we call as bipartite graph. Suppose that you are having a graph like this. One is connected to two is connected, one is further connected to 3, and 2 is connected to 4, suppose. Is it bipartite? Is it bipartite? Okay, how do graph coloring work? See for here, if any two nodes, suppose that 1 and 2, they are sharing an edge, right? And you are given only two colors. Let that be color number 0, color number 1. If you have colored node 1 with color 0, right? You cannot color node 2 with color 0. That's not possible. The separate color has to be utilized. If any two nodes U and B are sharing an edge, both cannot have the same color. That's how graph coloring works. Fine. So can I paint the entire graph that has 4 nodes right now that are having the edge structure like this, utilizing two colors? If I can, then that's a bipartite one. If I can, then this is a bipartite graph. Else it is not. Else it is not. All fine? All fine? First tell me this. Is it all
Yes.
fine? Okay, now is it possible to color this?
Hmm.
Is it possible to color this? I can color node number 1 with the red color, suppose. Two colors. Let that be red and yellow. Okay, then I think node 2 and node 3 has to be colored with a separate color. For sure. All of you agree? And then node number 4 has to be colored with a red color. I am bound to do that. It's sharing an edge with the yellow colored node. So it is, we are left with the choice to color it with red only. Okay. All fine. Okay. Let's see as per the example. So this is a bipartite graph as per our analogy. So let's see whether I can try coloring this particular graph with two colors or not, right? How they are being connected? 0, 1, 2, 3, right? All are having an edge in between them, and 0 and 3 is also connected. Is it a bipartite graph? Tell me that.
No.
So 0, I can try coloring node number 0 with color C1. Accordingly, node 1 and node 2 should be colored with C2. All of you agree? All of you agree that accordingly 2 and 1, since they are sharing an edge with node number 0, they has to be colored with color C2. So
Yes.
accordingly, as per node 1 and node 2 again, node 3 needs to be colored with what? C1, because 2 and 1, whatever nodes 2 and 1 we are having, they are colored with color C2. Only one color we are left as a choice with. What is it? C1. And that has to be used to color node number 3. But 3 also shares an edge with node 0, which is further colored with color 1. That means neither I can color this particular node with C1, neither with C2. Neither with C2. So that's what this particular node cannot be colored at all. So that's why this particular graph is a non-bipartite graph. Works?
Yes.
Okay, how would you judge this, by the way? How would you judge this? Suppose that I'm running a BFS, then how would you judge this, whether the graph is bipartite or not? 0 is connected to 1, then 0 is connected to 2. 2 further is connected to 3, 3 is connected to 1 again, and there is an edge between 0 and 3. How would you judge this? Let's suppose I started off from node number 0. Color this with color C1, suppose. Okay. And from 0, I'm running a I'm running a DFS, step first search, whatever. DFS, BFS, anything is gonna work here. Don't worry on that. Let's try with DFS initially. Correct. I started off with 0. From 0, suppose I visited 1. I visited 1, right? I visited node 1 from 0. Let me color that with a separate color. I know that 0 has been colored with a green color. Node 1, whatever is its neighbor, correct, needs to be colored with a different color. Let's color it. Okay. From node 1 onwards, right, only one color is there that has been unvisited. Am I correct? From node, only one unvisited node is there. What is it? Node 3. Node 3, right? Okay then. So you would definitely visit node 3 here and color it with the green color. All fine? All fine? Okay then. From 3 again, right? Right now I'm standing at 3. What are the nodes you may try visiting from?
2.
Here? Anything else?
No.
Okay, fine. Let's go to 2 back, right? Let's go back to 2 by the way. Let's go to 2 first, and I would definitely color 2 with a blue color, whatever I'm utilizing. Okay, then definitely after coloring 2, I would be back at 3. Am I correct?
Yes.
Okay, from 3 onwards, you would definitely at least have a look that 0 is the neighbor.
Mm.
Is it that even if it is visited, it is a neighbor of mine. So I would definitely at least iterate over that. Iteration will be there, right?
Mm.
And after the iteration, I am trying to see whatever is the color with which 3 has been colored, with the same color 0 has been colored as well. And neighbor is sharing same color. Right? You are standing at a node 3. You are trying to visit all the neighbors, right? One was its parent. Definitely it has a different color, for sure. One was its parent. Definitely it has the different color. Right now, if I go from parent to the child, child would be colored on a different color. That's what is the analogy with BFS we are following. Correct. Then from 3, you have another node 2. Node 2 has not been visited yet. I colored it in green. No problem. Then again from node 3, I came back to exploring zeros. There is neither the parent of mine and but has been colored. And what is the color? This is also green. The current node is also green. So corresponding to any node you are visiting, if any of its neighbor n, right, has been visited already, has been colored with the same color as that of u, I would immediately return false. Correct. Standing at the current node u, it shares an edge with another node n. Node n has been already visited by another node x. And due to the nature of node x, the node n has been colored with color C1, whatever node u already shares. So this is not a possibility. This is not a possibility. Due to the nature of parent of node u, that was somehow, let's call it as V, I had to color it to C1, right? V was being colored, whatever was its parent, in C2 suppose. From V, I visited you. What was unvisited so far? You are visiting because it is unvisited. Correct? You have visited that and colored it with different colors C1. Now the neighbors of you are exploring. Whatever non-visited ones, I colored them with different color. That's it. Whatever are the visited ones, let that be another node n. This node n has been visited by another node x, suppose. Its parent x. And due to the nature of parent x, it has been also colored in the same color s. Whatever node u has been colored off with already. So two neighboring nodes cannot be sharing the same color. If such scenario occurs, straight away return false. If you are able to visit all the nodes, no particular this scenario has occurred at all, at the end return. Is it understandable for the first hand? Tell me that.
Mm.
Is it understandable? Let's see by the way. How would you code this? You are given the graph only, right? That is what they have given in terms of C4 here. They have given you the entire list of values, maybe 0th node. Into the 0th index, it is containing nodes 1, 2, and 3. 0 is connected to 1, 2, and 3 all. So that's why a list of values has been given to you. Then I think node 1 is connected to node 0 and 2. Then again, node 2 is connected to 0, 1, and 3. So entire adjacency list they have provided here, right? In terms of the graph. So how should we proceed ahead with? How should you proceed ahead with? Tell me that. Let me make a DFS function. Returned whatever DFS is returning. Works.
Mm.
And I can just say that run to all the loops by the way, but they are not giving me that how many rows or number of nodes are gonna be. So let that be. How can I just say that how many nodes are gonna be there? It would be equal to that of graph.size. Works. How many, whatever number of rows will be there inside the graph, that is equal to the number of nodes. Correct. Let's say that from the there can be multiple components now inside the graph. So let me try running from 0, I less than n, I plus plus, right? I plus plus. How would you maintain that? So let me just say, let me maintain with the visiting and non-visiting nature should be maintained in terms of color. Can I just do that? If a node is colored, then that has been visited. If not, that has not been visited at all. Correct? So I can just say that vector of integers, let that be. And let there be the analogy 0 and 1. 0 is a color, 1 is a color. Ultimately, that's what I can represent for a bipartite graph. Vector of colors, let us suppose. It's gonna be for n, and initially let all of them be filled with -1. Works? Okay, then what should I proceed ahead? If suppose color of the node I it is equal to that of -1. Then run DFS. Then run DFS, right? And the DFS further would be returning true or false, whether after performing the the current DFS traversal on a component, I am able to color all of them or not. If I am able to color, then if I'm not able to color all of the nodes in the current component, I would be returning false. So I would just say that if DFS starting from the node I inside the current component, given the color vector, whatever we are maintaining, right? Okay, fine. And as well as the graph, the entire adjacency list I need to pass on. If it is equal to that of false, straightforward return false from here. No further checking is required. Okay. No further checking is required. That's it, maybe. That's what we may be fine with. After the loop, right? From inside the loop, after performing all the coloring operations, if you are able to color all the nodes inside the graph, then at the end return works. Let that be the initial analogy. And let's try going ahead with our DFS approach. So let there be bool DFS. What you are going to do here? Tell. So I require the node initially, and we require vector of integer, right? Color. Vector of integer color. Then what will happen? And let that be the same color vector, right? Whatever we have declared inside the bipartite function. So let that be the alias. And then what I should do afterwards? Okay, we have to pass on this graph. Let's not make the copy, but let's point to the same graph, whatever has been passed on into our original function, right? Let's do that. Okay, then what will happen afterwards? Tell. What should I do? Okay, fine. Another thing I would require to keep, what is it, by the way? What is the current color I am dealing with? Anti-call. What is the current color using which you are trying to color the node, right? That's what I require. So let's start off initially coloring a separate component, right? Whenever you are starting with the separate component of a color, let that be always with the value 0, right? Okay, then. So whenever I am visiting a particular node, let the color of the node be colored with a given color, whatever we are doing. Okay, then what? Afterwards, what then? Tell. Afterwards, what you may try doing? Explore all the neighbors for int neighbor that is residing into our graph of node, wherever it is, right? Then what you are going to do afterwards? Tell me that. What will you do from here? What will you do? Tell. If suppose color of the neighbor is equal to that of -1. It has been colored with -1, right? I can try coloring it. Go ahead and perform the DFS traversal on the given neighbor. Try coloring it from the neighbor onwards. I can just say color it with color ZOR1. Will it work? If the current color you are dealing with is 0, it would be changed to 1. If it is 1, then you would just convert that to 0. Will it work? Just take a bitwise ZOR with 1. That works. Then color array would be passed on as it is, and I would be saying that graph would be passed on as it is. Works? Works or not? So if you are trying to perform the DFS traversal, right, it has to return something. You are trying to perform the further coloring from the given neighbor onwards. If you are getting a false operation overall, that if I go to this neighbor, right, I'm getting at least a false case of coloring. A node at least cannot be colored. So if that's the case, from here onwards, return false. From here onwards, return false. Okay, what else? What else I may try doing from here? If the color of neighbor is equal to -1, I tried coloring it with the help of a DFS operation. If I'm unable to do that, it's giving a false operation, then straight away I would be returning false. No further checking is required. Else, right? Suppose that the current neighbor is colored already. The current neighbor has been colored already by some other parent. What should I check here? What should I check here? Else if color of the neighbor, right? If it is equal to that of the current color, whatever with which the given node, whatever I'm visiting, is getting colored with. Neighbor neighbor has been already visited and colored with a color of the given node's color with which we have colored it. Fine. If it is so, then also straight away return false. Works. Then also return false. In both of the cases, I need to return false. Anything else? At the end, if all the neighbors have been successfully visited, at the end, I can just say return true. Works. Works. And yeah. Works or not, first tell me any doubts with the DFS you are having. If you are visiting a node, color it with the given color. You cannot visit that, right? A node can never be visited with a DFS call unless and until it is not colored. If it is colored, no more DFS call would be made here. It's just that if a particular neighbor of the given node has already been visited, you would just check color of the current node is same as that of current color of the current neighbor I'm exploring. If it is so, return false. Two neighbors can never share the same color. If they are different, all fine. Nothing needs to be done. Go back to the next iteration. If all of the things are correct, return true. If either of the case fails, return false. That's it. That's it. And there can be multiple components here. So try judging that starting from the ith node, whatever components we are having, right? Or whatever component we are having inside that, whatever nodes you are having. If you fail to color either of them, return false straightforward. If either of the component is failing, return false straightforward. Else return true at the end. That's it. We don't require anything else, I feel. Let me try running this. Let's see whether we are able to do that or not. Okay, both the cases has passed on. Try submitting. Let's see. Is it accepted? Any doubts?
Clear.
So we have just ran DFS on the entire graph. Nothing else, I feel. Anything different we have done? All the nodes have been visited at most once, not more than that. With the help of DFS calls, any of the node has been visited at most once, not more than that. So overall, the time complexity comes out to be big O of B plus C. Okay, works for everyone?
Yes.
All clear so far, whatever we took today? Some DFS and BFS based problems. All clear? All of you can do that on your own as well. Try a few more problems on Leetcode, right, on your own. And let's continue from the next day.
Okay.